What we have been doing in this second half of the course is to study analysis techniques to be able to judge how efficient or inefficient a specific algorithm or a piece of code given to you is. We started by looking at iterative techniques or iterative code and its analysis. We covered three topics: analysis using summations, amortized analysis, which is only applicable on amortized algorithms, and randomized analysis, which is only applicable on algorithms that involves some kind of a random process. What we will start looking at today is analysis of recursive code. We will look at three techniques: recurrence trees, master method, and Akra-Bazzi, and we will see how we can approach finding the asymptotic behavior of any recursive code. So here's an example of a recursive function, the factorial function. You've learned the factorial perhaps since your elementary school. You know that the factorial of a number is the number itself multiplied by the factorial of the number before it. So 5 factorial is n multiplied by, or 5 multiplied by 4 factorial. To calculate 4 factorial, you multiply 4 by 3 factorial, and it goes like this. So this is, by definition, it's a recursive definition. And you have seen this piece of code that shows up in the slide, where we do factorial computation using recursion. Now, the problem with this piece of code, if you look at it, is that you cannot write a summation for it, because summation involves counting the number of steps. But here, inside the summation, you need to present the summation that is nested within the summation. So basically, you would like to represent recursion. And it turns out that you cannot have recursive summations. It doesn't work. Okay, it's not defined mathematically, because when we count the number of steps, we would like to be counting them in a deterministic fashion or in a sequence. So that's not the case, obviously, in recursion, because there is no for loop here in the first place, or there is no looping constants at all. So we will look at the three techniques that I mentioned in the previous slide, just to be able to analyze any piece of code that involves recursion. And consequently, from now on in your career, once you're given a recursive code and you're asked what's the big O of this, then you'll have to think of one of those three methods as the tool to use to actually get the big O of that piece of code. Now, what we're actually going to do is we will use what's called a recurrence relation or a function, which is, again, it's a mathematical technique to talk about the performance of a recursive piece of code like the one in front of us here for the factorial. Okay? Now, recurrence relations or recurrence functions is the mathematical equivalent of recursive code, in the sense that in the right-hand side of the definition of a recurrence relation, you will see the same function you're trying to define. And that's what you will see here in these two examples, okay? And you will also see as a recurrence relation a definition that does not involve a recurrence or recursion. So it matches perfectly, basically, with recursion. So if you like, read the first example. It says t of n is equal to O of 1 if n is equal to 0 or n equal to 1. Else, t of n is equal to tn minus 1 plus O of 1 if n is greater than 1. Okay? Now, if you look at the second line, which I just read, which says t of n equal to tn minus 1, that's exactly what recursion is about. Okay? You're trying to define something, but you define it in terms of itself. And that's what recurrence is actually giving you. Okay? So recurrence is a valid mathematical technique. It's a valid mathematical function, what you're looking at here. And it is defined in the way I am telling you about. You'll have to have two versions of it. One version that involves the recurrence on the right-hand side, and the other version will not have the recurrence or the recursion on the right-hand side. Okay? Now, in general, of course, I could generalize this example to the one at the bottom, which says, the time to process n input is equal to some constant. Doesn't have to be exactly 1. It's some constant if n is equal to 0 or n equal to 1. So if the data set given to me consists of 0 elements or 1 element, I will spend some constant effort. Else, if n is greater than 1, so I will spend some time processing n minus 1, okay, plus c, plus some constant effort. Now, obviously here, this will look like playing with the words to you in the first time you look at it, because you say, okay, yeah, sure, this is a valid recurrence, but what's the big O? And actually, this is not the solution. What you're looking at is the representation, a mathematical representation, a one-to-one mapping between the notion of a recurrence function and the recursive code. But we didn't start solving the recurrence relation. So we will solve recurrence relations to pick the big O. So obviously this is not the solution. It's not valid. I cannot, cannot tell you like, what's the big O of factorial? What's the big O of factorial? So you tell me, oh, T of n is equal to a constant, O if n is equal to 0, O is equal to 1, and T of n is equal to Tn minus 1 plus some constant effort. That is not an acceptable answer. Okay, you cannot state this in terms of a big O of something. Okay, so you cannot tell me it's O of constant if n equal to 0 or 1, or it's O of Tn minus 1 plus c if it is not, if n is greater than 0, greater than 1. Sorry. Okay, so you cannot say that's an answer. So what we're going to do is we're going to study the given recursive code, and we will develop a recurrence relation that will look like the two examples here at the bottom of the slide, and then we will solve that mathematically to be able to achieve or reach to the big O. The first technique we're going to look at is called the recursion tree method. Now, what we're going to do in this technique is we are going to expand, or simply stated, trace through the recursion and build a tree starting from the first call to the recursive method being at the root level, and expanding this tree by creating children nodes at every level as long as we keep into recursion. And at the bottom of this tree we will hit the base case. Okay, so I want you to imagine we have a recursive code, and we're going to call this recursive code, this recursive function we're trying to analyze. What happens in recursion? We keep calling the same function itself over and over until we hit the base case. So what we're going to do is we're going to study, or basically calculate, the amount of effort we're doing starting from the root, from the first call, all the way till we hit the leaf. If we can compute that, then we have found the big O of this function. I'm just giving you a hint of how this works. We will see examples. By the way, in some textbooks this will be called recurrence trees. Okay, so either it's called recursion tree method or just simply the recurrence tree. So let's study again merge sort, which we have discussed when we were doing divide and conquer. Let's try to analyze the performance of merge sort. I already told you then that merge sort is n log n. So let's see how actually we can come up with that term, given the fact that merge sort is a recursive algorithm. So recall how merge sort works is that we divide the n element sequence to be sorted into two subproblems, each of size n by 2. How do we do the division? We just pick the value in the middle. We split the big array, say of 100 cells, into two smaller arrays, each of 50 and 50. And that's the divide part in the divide and conquer. We sort the two subproblems, or the n by 2 array and the n by 2 array, using merge sort. And then finally we merge our two sorted subarrays into one bigger array. Let's again see the simulation for that. So this is my starting array. I start with an array of unsorted values: 99, 6, 86, 15, 58, 35, 86, 4, and 0. I will pick a cell in the middle, and I will divide this into two subarrays. That's what you see here in the slide. Now obviously there is always an issue if the number of cells is even or odd. I can always resort to integer division to figure out where is the middle of the array. Now, thinking divide and conquer again, this is still complex enough. I don't like to sort that because I'm going to do lots of work sorting. So I will try to trivialize the problem even more by splitting these two arrays into even smaller ones. That's what you get here. I've split each one of the two arrays into even two smaller ones. and I will not stop here, I will continue doing that until I have an array of one element. And because the number of cells given in the array or the n was odd, so I will end up doing that even one more time to split the 4 and the 0 array into an array of 4 and an array of 0. For me, there is no more trivial than sorting an array of one cell, because an array of one cell is by definition sorted, because there's nothing bigger than it and there is nothing smaller than it. So I have stopped at the base case where I don't need to do any further division, because it doesn't make sense to do any further division, because I can solve this trivially, which is basically return the array itself. Now, the merge step involves combining the solution to my sorted subarrays, each of one size, of size 1, into a bigger array where I merge the values in the right order. So 4 and 0 will be merged to be 0 and 4, and consequently 0 and 4 and 86 will be 86, 0 and 4 will be merged to be 0, 4, 86. And 58, 35 will be 35, 58, as you see. Okay? And the rest is the same. I'm merging and putting the elements, the smaller first and then the bigger. And I continue on merging my sorted subarrays to create an array of size 4 and an array of size 5 that's completely sorted, and then I measure those two big subarrays into my final subarray. This is merge sort. We have studied it before, and I'm sure you've seen this before. Now let's try to do the analysis. Before we do the analysis, this is not what you will be given. What you will be given is a piece of code that looks like this. What is required from you to be able to derive the recurrence relation is to understand how the data is being reduced. So if you look here, the code is self-explaining itself, basically. Mid, I got an array of size n, array A, and then I take length of A divided by 2, and that would be my midpoint. So what that means is I am given an array of size n, and I've split it into two halves, n by 2 and n by 2. Why am I saying two halves? Because this is what the code is saying. The left will have one half, or L will have one half from 1 to mid, and R will have the second half from mid plus 1 to n. Okay? And then the rest is the problem we were living with here, which is that we have a recursive code. So I'm basically recursively calling the same method merge sort. I will merge sort L, merge sort R, and notice that the same logic will apply when I go in with L instead of A. I will split it to two halves, and one half will be assigned to that L inside the new method call, or the new invocation of merge sort, and another half will be assigned to R. Okay? And when I come back from the recursion after going into merge sort of R and L and R several times, I will call a method called merge, which takes L and R and A. Okay? Now, why am I being very detailed in explaining the code? Because this is what you will be given, a piece of code, and you will be asked, if you're asked to do an asymptotic analysis, since this is recursive in nature, you will be asked to come up with the recurrence relation. In the recurrence relation, what I will have is a base case and a recursive case. The base case is easy, obviously. Even here it's easy. If the size of A is equal to 1, I'm doing nothing. So it's going to be, T of n is equal to a constant if n is equal to 1. My problem is finding out the recursive case in the recurrence relation, and that will require me to understand the code carefully to understand how the split of the data is made and how many splits I have and how much effort I'm doing after I do the splits. How many splits I have? I have two, one assigned to L, one assigned to R. How am I dividing the data between those two splits? I am doing half and half. What else I'm doing when I finish the recursion? I'm doing the merge. If you go and check the code for the merge from the early slides, the merge actually takes L and R and merge them together from left to right, which means it's O of N. Because I have to pass through all of L and all of R to produce the output, which is the sorted sequence that with the content, with all the content of L and all the content of R, so that's O of N processing. Okay? So this is what shows up here. In my step 1 to do recurrence analysis, or basically building the recurrence tree or applying the recursion tree method, I will have to find out the recurrence relation. So this is what I was just describing. T of n is a constant if n is equal to 1, because when we reach to an array of size 1 we do nothing, we just return it. Else I am creating two splits, the L and the R, that's why the 2, and then it is n by 2. The division of the input is I'm dividing the input into two equal parts, n by 2 and n by 2, and I have basically one n by 2 and another n by 2, so I have 2 n by 2, and that's what you see here. The time to process n inputs if n is greater than 1 is 2 multiplied by the time to process n by 2. I hope this has been, I was able to communicate it clear. That's why I have a 2, because I'm dividing the input array to two parts, each is of size n by 2. Now you might ask, if you have never seen this before, like, okay, can we have other variations? And the answer is yes. It's up to the developer of a recursive algorithm what they're really doing in the code. So you might find yourself doing weird stuff, or finding, not you, but you might actually come up across some weird algorithm that is recursive, that is doing 3tn by 8, for example, which means the algorithm is dividing the data into 8 equal parts, okay, and it's picking 3 of them. That's why 3 to n by 8. But what we have here is that we are saying, again, the time to do n is 2 multiplied by the time to do n by 2, because I have two splits, or two divisions, and each one is of size n by 2. Plus the merge step at the end. To merge, I always gonna do O of n, because I have to pass through the array from beginning to end, or all of L from beginning to end, all of R from beginning to end. So that's theta of n for sure. That's why I've written it as theta, not even O. It's for sure guaranteed you're gonna go from the beginning to the end. So that means theta of n. Okay? Now, this is the first step to do a recurrence tree. Okay? And this is a very important step, because everything that is coming will depend on this. So let's see what's coming. So what I'm going to do is I'm going to start building up the tree. I will use my recurrence relation. What did I say? I say that the time to run this algorithm is 2tn by 2 plus theta of n. I will put the term that does not have the recursion, which is the t, I will put it at the root. So that's what you have here, cn at the root. And then I will create children as many as I have divisions. So I have two divisions, L and R, each takes n by 2. So I've written, or I've created two children, each is doing n by 2. Now I won't stop here, and what I'm going to do is I'm going to expand further to 2tn by 2 and the other tn by 2. What am I trying to do here? What's the issue? The issue is I'm going to build a tree, and then later on, after I have built the tree, I will calculate the total effort done in the tree. Okay? You already see some effort, where at the root here, at the left, in the tree in the left, you see cn or n. Here's an effort. Here is something concrete we know about, what we are going to do, which is the merge. Okay? But the problem is tn by 2 and tn by 2, these are not nice terms to look at. and these are not helpful terms to be able to reach the big O because I have a t. I define big O or big theta or big omega in terms of n, not in terms of t. So I need to get rid of this tn by 2. So I'm going to do the following. I will imagine that actually the code the data I'm giving is not n, it's n by 2. And it's the same algorithm. So I will substitute n by 2 into my recurrence. Now if I substitute n by 2 into my recurrence is going to be, each one of those will expand, as the arrows show, into a whole tree. The recurrence is going to be 2 tn by 4 plus n by 2. So I'm going to put that instead of tn by 2. This whole tree, as you know, the arrow shows, is a replacement of tn by 2. Let me actually try to label it here. I will put a red circle around it. So this one that has the red circle is the replacement of tn by 2. How did I get this replacement? I just substituted in the recurrence. When you substitute n by 2 into the recurrence in the previous slide, you will get 2n by 4, because I was already dividing by 2, so now it's going to be 4. Okay? And plus it was theta of n, now it's going to be theta of n by 2. So I'm just going to take all of that equation and plug it in instead of tn by 2. And I'm going to do that to the left side and the right side. So this is now my picture, but I'm not done, because tn by 4 also is a term I don't want to see. I want to just remove it from the tree. And that's what I'm going to do next. I will substitute tn by 4, no, n by 4, sorry, into my recurrence. Okay? So it's going to be 2n by 16 plus n by 4 for the merge. And again, I don't like tn by 16. I will take that and substitute it back into the recurrence. So it's going to be 2n by 32. And this keeps going on. Now, forever, are we going to run into an infinite loop? And the answer is no. Because ultimately, in the base case, you have to have reduced the data that you're working with so that you say there's nothing to be done, because there's no data. That's very clear in the merge sort case. You know, if n is equal to 1, there's nothing to be done. I'm dealing with a constant. It's a one term. It's an array of size 1 is sorted, so I'm just going to return. Okay? Now, so what that means that this tree, you can continue expanding it as much as you like, but at the bottom of the tree, you will reach to a constant. In the case of merge sort, it's going to be 1. In the case of other algorithms, it might be something else, but it doesn't matter. It's going to be a constant. Okay? What I'm going to do next is I will label the levels just to be able to do the manipulation we're going to discuss. So first level at the root level is level 0. Second level is level 1, all the way till the last one where there are constants all over at the leaf level. I'm going to call it level H. What I'm going to do afterwards, I'm going to count the number of nodes in every level. So at the root level, at level 0, I have 1 node. In the second level, or in level 1, I have 2 nodes. You can just eyeball them, okay? In level 2, I have 4 nodes. There's Cn by 4, Cn by 4, Cn by 4, Cn by 4, that's 4 of them. Okay? Now, at the bottom where I have an array of size 1, I must be having n nodes, because if my array has 100 cells, and I say I bottom the the recursion, when I am at size 1, then I must have hundreds of them. I must have 100 of them. If my size is n, and I stop the recursion every time when I reach to a size 1, and I'm saying I'm starting with an array of 100, so at the bottom level, if I count the nodes, I must n of them. I must have the 100. Okay? What I'm going to do is, next is I'm going to multiply the total effort I am doing in every level. So first level is n, second level is n by 2 plus n by 2 is n by 4 plus n by 4 plus n by 4 plus n by 4 is n, and it goes like this. So now I know how much work I'm doing in every level. Now, to do the manipulation I'm going to show you, I will express the number of nodes in every level as a power of 2. So the number of nodes in the first level is 1, that's 2 to the 0. Number of nodes in the second level, which is level 1, is 2, which is 2 to the 1. Number of level in level 2, number of nodes in level 2 is 2 to the 2, which is 4. Okay? Now, number of levels in the last level, regardless of where that is, and how far we went down, but for sure at the last level, we said we have n nodes, which means it's going to be 2 to the h, because the power in each one of those two terms between brackets was actually the level index. And that's why I started from 0, so this will work out nicely. So again, at level h, I have n nodes in my tree, in my recursion tree, and that is equal to 2 to the h. What we will do next is to try to sum the effort we're doing in all the levels. As we've noted, each level we're doing n effort, or O of n effort. However, there is something interesting here. The division is really perfect, because every time I split into two halves, but consequently what I'm doing at every one of those halves is half the effort I've done in the previous level. So when I add up, it goes back to n. Like the difference between n by 2 and n by 2, I'm going to do n by 2 effort and n by 2 effort, which is n. And then I go and take n by 2 and split it further into two further halves, so it becomes n by 4 and n by 4. And now I have 4n by 4, which is again n. Okay? So I'm now confident that in every level I am doing n effort. So if I would like to find out the total cost, or the total work I'm doing at all levels, is basically, which means in the whole tree, I will multiply the number of levels by the cost of every level, which is n. So the question becomes, what is the number of levels? And since here the division I'm always splitting into two halves, you know from your early computer science courses is that when we are given an input and we split it into two halves, and we deal with every half separately, what we are doing is that we are quickly reducing the size of the input, reducing the problem total size so fast that we can say that this is a log n. And exactly, that's what we're going to do. Is specifically in the case of merge sort, we're going to get log n levels. Okay, so the h at the bottom, level h, is going to be equal to log n. Now, so what's the total effort done here? It's how many levels we have. We have h levels, which is log n, plus the first one, okay, multiplied by the cost of every level, which is n. So that will be n log n plus n. So n log n as a term will dominate, so we will say it's in theta of n log n. This is by a little bit of intuition. I will show you a more systematic way later on. So, to summarize, the recurrence method, or the recursion tree, or the recurrence tree can be used on any recursive code. Okay? The problem is, which is not really a problem, it's a requirement, that you need to understand how the recursive code is dealing with the data. How many divisions it's making, and what's the data passed to every division. There are two separate things here. The problem always with merge sort, that's why I'm going to show you, in the coming example, a completely different kind of recurrence. You can see it at the bottom of the slide. The thing about merge sort, it's perfect to use to start with, in explaining recurrence trees, because the division is perfect and it's very nice and simple and easy to understand. You know, it's 2tn by 2. I'm creating left and right, as I mentioned before, and each one takes half the data, okay? But that's just because merge sort is so nice, okay? But we will see other variations. So your first challenge will always be come up with the proper recurrence. If it's given to you, then you're quite ahead. You just need to apply the technique. So I will show you now a summary of the steps you need again before we start seeing more examples. So here are the steps to construct such a tree. Now, the first thing is, my starting point to be able to construct the tree correctly is to look at the code, understand it carefully, and write down the recurrence relation. How the processing of the data is being done. Any recursive piece of code will stop at the base case because there is nothing to be done. And if there is nothing to be done, that means there is no data. So we are reaching at the leaf level to the point where there is no data. And at the root level, we had all the data. So a crucial step in building the recurrence relation is to understand how the data has been reduced from the first call all the way till the call where we hit the base case. After that, we will write down the recurrence relation. This will be step number 1. Step number 2, we are going to draw the derived recurrence as a tree with the recursive terms at the leaf level. We are basically going to grab the recurrence relation and use it to construct the tree. This is the simplest approach that we could use, and it works greatly, as you will see. Now, what I'm going to do is I will keep replacing the recursive terms at the right-hand side in the recurrence relation at the leaf level by their equivalent right-hand side. Okay? By resubstituting in the derived recurrence. Just hold on with me one slide and everything will be clear. But what I'm telling you is I will get the recurrence relation, we will draw it in a certain way, and then we will keep substituting or erasing part of what we have drawn and substituting it with a smaller version of our recurrence relation. And we will keep doing that until we hit the leaf level. What we will do next is that we will count the number of nodes in our tree at each level. Level 0, level 1, level 2, level 3, level 4, level 5, all the way till the last level at the bottom. I'm just going to count horizontally how many nodes I have. And then I will calculate how much work I do on every level. Okay? And we will play a trick with the last level because this is where we hit the base case. And then finally, we calculate the sum of all the work we have done. So let's see this example where, I'm not showing you the code, but I'm showing you the recurrence relation that was obtained from the code. Now, if you look at this obviously, requires some thinking. What this recursive function was doing, it was dividing the input into 4 parts. So since it's n by 4, four, supposedly equal parts, a quarter and a quarter and a quarter and a quarter, and we're speaking 3 of them. And apparently 1 quarter just disappeared. And then at every one of those steps, it was doing O of n squared effort. That is a theta of n squared, which means it's always doing that. It's in theta means it's omega and it's O, so it means it's always doing it, okay? So I'm just going to apply my steps that I was mentioning to this recurrence relation to try to expand this recursion, the execution of this recursive function, all the way till the leaf level. So again, I'm not interested in this 3tn by 4. It is going to cause me trouble because I would like to reach to an answer that it is in O of some n squared, n to the 7, n log n, whatever, but not t, okay? So I will take the right-hand side of this recurrence and draw it as a tree, as I already mentioned before. Now, the root of the tree is going to be n squared, which is the effort I'm doing, plus coming out from this root, 3 children for the 3, each one is doing n by 4 work, okay? Now, this is just a way to write the recurrence at the top. this is not enough. We will continue expanding this. So I will take n by 4 and plug it in back into the equation you see at the top right. So instead of where it says Tn equal to 3 Tn by 4 plus theta of n squared, I'm going to take n by 4 and plug it in there instead of the n. So if I plug in n by 4 into n by 4, this becomes n by 16. Okay? So now this will be my picture. This is my picture now. Okay? I plugged in n by 4, and instead of the Tn by 4 in the left tree, I plugged in n by 4, and I substituted in just in the equation. So it was n squared. When I plug in n by 4, it's going to be n by 4 all squared plus the 3 Tn by 16. That's why you see 3 children coming out from n by 4 all squared. And I had 3 of those. I had 3 Tn by 4 in the tree to the left in step 2. So I will do that 3 times. I'm basically expanding the tree in step 2 to the figure you see now in step 3. And then this will move on to further expansion. Okay? So I will further expand because I don't like Tn by 16. So I'm going to take n by 16 and plug it in instead of n. So it becomes 3 n by 16 multiplied by 4 plus n by 16 all squared. And that's what you see at step 4. Now I don't want to keep doing that. Obviously, I could do it forever. So I know that ultimately I have to bottom this tree, which means I have to reach to a naive base case where I stop the recursion, and I will stop the recursion here. The assumption is I will stop at the base case. I'm doing some constant work. I don't know exactly what is that work. Is it 7 steps, 10 steps, 50 steps? But it's going to be some constant work. Okay? So this is now my tree that appears in step 4. Now, what I need to do again, I will number the levels, count the number of nodes in the levels, express that count as a power of 2, and label the last level as level H. And I will again look at the amount of work I did in each level to be able to figure out how much work I did in the whole tree. And that's what you see in this slide. I again number the levels starting from 0. It helps me to start from 0 all the way to level H at the bottom. I'm counting the number of nodes in every level. Okay. Now, notice here I'm expressing it as a power of 3. Why? Because I have 3 branches. So in merge sort we express it as power of 2 because we had 2 branches. So how we express the number of nodes in every level is based on the branching. Okay, the branching here is 3, so it's 3 to the 0, which is 1, 3 to the 1, 3 to the 2, 3 to the 3, which is 9, and so on. That would be the number of nodes we have in the tree horizontally. Okay, at the same level. Now, I will calculate the amount of work I'm doing in every level by multiplying how many nodes I have by the amount of work I do at every node. So I have n squared at the root level, level 0. I have only 1 node, so it's 1 multiplied by n squared, which is Cn squared. At level 1, I have 3 nodes, and in each one of those 3 nodes, I am doing n to the divided by 4 all squared. So I will keep the square with the n, I will take the 4 out, so it becomes 16, and I had the 3 for the 3 branches, so 3 by 16 Cn squared. Now the next level becomes 3 by 16 squared Cn squared. Okay? And it goes like this. Now we will see the trick I mentioned in the steps. If you look at the last level, level H, how much work I'm doing? Well, I want you to look at the bottom of the tree. There is a statement that says 3 to the h equal to 3 log n base 4 and so on. So this is how we do this. We said we're going to call the bottom level level H. And then we know how many nodes we have here. since I'm stopping at a trivial case, I will assume that every node has one element. So how many I have of these nodes? I will have n of them. We've already reached to this conclusion with merge sort that n is going to be equal to 3 to the h. In merge sort it was 2 to the h. Okay? Again, at the bottom level I reach the base case. In the base case, this is the trivial case. In the trivial case means there is no data to work with, so I will assume the data size is 1. If I have an array of 1000 elements and I'm saying that I'm going to hit the base case when the data size is 1, how many times I'm going to hit the base case? 1000 times. And in every one of those cases, 1000 cases, what was the size of the data? It was 1. Since this is what I'm trying to represent in the tree, okay, I will have 1000 of those nodes at the bottom. And every one of them I will have one data entry, one data element. So if I say what is n, it's going to be the count of those that exist at the bottom. What is the count of those that exist to the bottom? It's 3 to the h. Okay? So n is equal to 3 to the h. Now, what is h? We've already discussed this, that, you know, because we're doing here perfect splitting in the sense that the recursion tree or the recurrence tree will never be skewed. We're applying the same formula at every level. So we're doing the same splitting at every level. What that means is the height of the tree is going to be logarithmic. It's log n, but the base of the log is related to the splits. Okay, it's related to the divisions. How fast are we divisioning, or how fast are we, how wide basically is the tree? Okay, so this is going to be, h is going to be log n, but base 4, not base 2. Okay, now 3 to the power of log n base 4. This is interesting, but it's not useful because I would like to express it in terms of n. So I can, and this is why you need to be good with logarithms, I can swap the 3 and the n. So it becomes n to the power of log 3 base 4. Okay? So the amount of work I do at the bottom level is theta of n to the power of log 3 base 4. Okay? Now what we need to do next is to figure out the total amount of work we've done in this tree. If you look at level 0, we were doing n squared. And if you look at level h, we're doing n to the power of log 3 base 4. So of the two terms, it looks like we started n squared and that started to decrease until we reached to some n to the power of log 3 base 4. So the total or the dominating term here is n squared. Okay, so this is actually how we do it by intuition. We can just, look at the first term and the last term in the level sum and decide which is bigger, and that will be the one that will override or will contribute to the biggest performance. I will show you later on a more systematic way where we actually put all of these terms in the level sum and solve mathematically to figure out what's the big O. That's if you care about, obviously, the constant beside the n squared. Like how much n squared? Is it like 50 divided by 99 n squared, or 76 n squared? Okay, they'll all be n squared, but if you really care about the performance, then you need to sum up all those level sums and figure out exactly how n squared, how much n squared. So one question I always get when I present these slides is, why base 4? Why not base 2? And I'm going to present it to you first by intuition, and then we will do it in a more systematic way. If you look at the recurrence at the top, it says Tn equal to 3Tn by 4 plus theta of n squared. The n by 4 is telling you, or the term that you are dividing by the n is telling you how fast the data is being reduced. You start with n, and at the bottom level of the recursion tree you have 1. But the question is how fast you reach the 1. This has to do with how much data is left. The less data you're able to work with in the new level while going towards the leaf, the faster you will go towards the leaf. In other words, if I start, let's put some numbers here. If I start with n equal to 100 and I'm doing n by 4, that means in the immediately next level I have 25. Because I've divided n into 4 divisions, every division is 25, and I happen to be picking 3 of these 4 divisions to continue to work with. But notice I went from 100 to 25, and then I will divide the 25 by 4 again in the next level. So the 25, divided by 4 is going to be close to 6. So you see, we are reducing the data very fast. Now let's imagine the scenario where we have n by 2. I start with 100. N by 2 means I've divided into divisions where every division is 50. It's not 25, it's 50, okay? Now I will divide n by 2 again, so 50 becomes 25. So you see, when we divided by n by 4, we were able to quickly reduce the number of elements we're working with compared to n by 2. So while the n by 2 and n by 4 will give you log performance because you are splitting the data continuously until you hit the base case where you're working with one element, there's a difference in the height of those trees. The denominator term, which is the 4 here, okay, the term you're dividing the n with, is actually telling you how short the tree is. The bigger the number, the shorter the tree, because the bigger the number, the smaller the data you take to the next level at the recursion tree to work with. Okay, so let's imagine n was 7, n divided by 7. Instead of 4, it's 7. Okay? If you start with 100, with n equal to 100, and you're dividing by 7, that's close to 13. While in the case of n by 4, it was 25. That's in the next level immediately after the root. Okay? So now your tree is going to be shorter, even further than compared to n by 4. So the denominator term is controlling how much of the data you pick to continue working with, and consequently is controlling the height of the tree. So to be accurate, we're not going to just say log, we will mention the base. If you're dividing by 4, it's going to be base 4. If you're dividing by 2, it's going to be base 2. If you're dividing by 7, it's going to be base 7. And this is by intuition, what I just mentioned. Now, let's look at it a little bit more systematically. Read the next point. It says, how far from the root do we reach 1? That's the same question I was posing, and I tried to answer by intuition. Now, the subproblem size for a node at depth I is n divided by 4 to the I. Okay? We've already deduced that from looking at the tree in the previous slides. Thus, the subproblem size hits n equal to 1 when n divided by 4 to the I is equal to 1. Or, you substitute or change the terms, the sides of the terms, or when I is equal to log n base 4. So you see, it's base 4, even using a systematic approach, which is n divided by 4 to the power of I equal to 1. Where am I getting n divided by 4 I equal to 1? The 1 is the size of the value of n at the leaf level. And n divided by 4 to the I is the number of nodes at the leaf level divided by the height, which should be giving me 1. Okay? And here is just stressing the same point, showing you the difference between different denominators or divisions of n. What's the impact on when does the tree bottoms? When do you reach the base case? If you're saying n by 3, and I'm just showing you here a big number, okay, as if you count the zeros here, this is a million. Log million base 3 is 12. Log million base 4 is 10. Log million base 5 is 8. Okay? So, why am I getting 8? Because the base is 5. Why am I getting the base is 5? Because I am reducing the data here faster, which is n by 5. I am picking 1/5 of the data, okay, at every level. So common sense wise, by intuition, it should also mean, that that tree height is going to be shorter, and that's even mathematically proven by taking the log. Now, here is the more systematic approach to step 7 that I have mentioned earlier. I told you that by intuition it looks like n squared because at the root level, at level 0, we had n squared effort, and then we were multiplying a fraction by n squared, and then ultimately we go to n to the power of log 3 base 4. So by intuition I know this is going to be n squared, okay? But you don't have to do it by intuition. You can actually work the math if you like it, or if you desire to prove so, and take out the fractions. And I'm not going to spend time on this how you do this. You should be able to do it. And this is a basic mathematical skill. And ultimately you will, if you look at the bottom, the second bottom line, it says 16 divided by 13 n squared, or cn squared, plus theta of n to the power of log 3 base 4, and n squared will dominate. And this is what I was telling you earlier. Now that you have seen the recurrence tree method, and the observation about it is that it's a bit tedious. Plus, imagine you're giving a piece of code and you're doing some development effort. You came across this recursive method, and then suddenly you're wondering about its performance. So you grab a piece of paper and start to draw the recurrence tree, and ultimately you will figure out actually what's asymptotic performance. But the question is there a faster way? And the answer is yes. We will look at 2 other techniques that are substitutes for the recurrence tree method, and they're much faster. So let's look at the master method first, which is based on the recurrence tree idea. You will see right away now that we will be doing a recurrence tree, but just to derive the cases of the master method. Okay? Now, this is actually the master method, or sometimes called the master theorem as well in some textbooks, is a kind of a cookbook approach to quickly find the big O, or the asymptotic behavior of a recursive piece of code. But the recursive piece of code that you're looking at, when you write a recurrence for it, you will still need to write a recurrence, okay? So you're still, you're given a recursive piece of code, you have to figure out the recurrence, and then you can use right away the master method, and instead of building the recurrence tree, which we have done with the previous 2 examples. But there is a caveat here. The recurrence tree, the recurrence relation that you come up with has to be in the format that is described here. You have to be dividing the input n by b, so you're making the input smaller, because as you see here, the b has an associated condition and has to be greater than 1. So if you start with n being 100, after 1 recursive call, now the n is less than 100. Okay? The only condition set is b has to be greater than 1. So obviously if b is equal to 2, you split the input into n by 50, or you created a division which is n by 50. Okay? Now the other condition is that the a, which is multiplied by t n by b, has to be greater than or equal to 1. Okay? So if it's equal to 1, you are really executing a slow recursive function, because you're not really splitting the data into 2 equal or more parts. You are splitting it into one part that is of lesser size. Okay? But that is acceptable. You can still solve this type of recursive function or method or logic using the master method. Okay? But remember, the b has to be greater than 1. If n is 2 or 3 or 4, if a is 2 or 3 or 4, well, that's even better, because now you have a nice split and you're actually working faster with the data. Now the other condition also that's associated with the master method is that f of n has to be an asymptotically positive function. Okay? So if you have instead of the plus and minus, that's not acceptable. It has to be a positive function. Now, the master method is actually a generalization of the cases we would find if we do a recurrence tree, given that we are building the recurrence tree using a recurrence relation that has all of these conditions we are actually putting forward. Okay? In other words, if your recurrence match these conditions, a is greater than or equal to 1, b is greater than 1, f of n is an asymptotically positive function, then you can right away jump to the master method and start using it. Okay? But if you are given a piece of recursive code and you write down the recurrence after you understand the code and logic thoroughly, and you find that the recurrence does not match these conditions. For example, a is 0.5. That will not match this. Okay? Or b is 0.5. That will not match this. Or f of n, there's something weird in the recursive function that makes it fluctuate, like sine n. Okay, so it goes up and down, or cosine, or tan. Okay, so it goes up and down. Then again, this will not be applicable. So let us build a recursion tree or a recurrence tree based on this recurrence relation. I'm just going to do the same steps we've discussed before. I will put the term that does not have the t, okay, that does not have the recursive part at the root level, which is f of n, and I will create these branches that I'm going to call them a branches, and each one of them is going to be tn by b, because that's what the recurrence I'm starting with has. This is the same like what we did with merge sort and the second example as well, after merge sort. Now we said what we do next is we expand this tree further, so I'm going to take n by b and plug it in the equation at the top, so this becomes a t n by b squared, okay, plus f n by b. Okay, so I'm going to call a again the branching factor. This is how many branches I will have. I will work this because this is a general equation. It's not representing any specific recursive code or a specific recurrence. This is a general formulation. I'm just going to describe this as a, and I will use this a term later on as usual. So again, this is the step I was just mentioning. I will replace n by b into my original equation, so I'm going to get n by b squared plus f n by b. I will take this right hand side term in the right hand side equation and replace it instead of, or put it instead of tn by b. And that's what you see here. I have now fn by b and a branches of tn by b squared. And I will do that to all the children of f of n. And that would be my step 3. Okay? I will continue doing that until I bottom this tree, which means I reach at the base case and I have a data element or a data size then of size 1. I have one data element. That's what you see here. I've bottomed what we call, this is how we describe it, you bottom the recursion. Okay? You bottom the recursion at the base case. In the base case, you're doing something trivial. It's all O of 1. And then I will go and do the same stuff I've described before, which is label the levels, count the number of nodes, and find the work in every level. So this is my step 5. I am now numbering the levels, level 0 all the way to level h at the bottom. And I'm just going to work with some level I here, since this is really an abstraction of the whole thing. So I'm just going to say that somewhere in the middle I have this level I, okay? And as you see here, the divisions n by b, it's always, the power of the b is the level number. So if n by b squared, then it's level 2. If n by b to the I, that must be level I. And ultimately we will see if n by b to the h, and it's going to be for level h. Okay? Now I will count the number of nodes. Remember with the merge sort example, we had the a was 2, so we used a power of 2. I mentioned that before. And then in the following example, it was 3, so we represented the number of nodes as a power of 3. Here we have the branching factor a is just a symbolic representation of how many ways we can branch, or the number of ways we can branch. So it's going to be a power of a. The first one is a to the 0, which is 1. The next one is a to the 1, which is 8. Second one is a squared, which is, a by a. That's what you see even here in the tree. And somewhere at level I is going to be a to the I. What is a to the I? Why do I mean by that? It's the number of nodes in this specific level. The level means horizontal in the tree. Okay, horizontal line in the tree. So it's going to be a to the I. At the bottom, when I bottom the recursion, I will have the number of nodes is a to the h, following the same way of thinking since we started a to the 0. Okay, we're just figuring out how many nodes we have at every level. Now the next step, I will try to compute the amount of work I'm doing in every level. So in level 0, I'm doing f of n. That's the only thing there. Okay. Now f of n here represents any positive asymptotic function. So this could be f of n equal to n squared, or could be n to the 3, or it could be log n. I don't care. Here I'm talking about it in a general term. So at level 0, I have f of n. Now what about at level 1? I have a multiplied by f of n by b. That's what I have here. Okay, I have a branches or a nodes, and in every node I'm doing work that's equivalent to f of n by b. So it's a multiplied by f of n by b. Now in the one after, it's going to be the same, a squared. I have a, because each one of those a's I split further into a set of a children, so it's a by a, so it's going to be a squared multiplied by f of n b squared. Level I is going to be a to the I, following the same logic, multiplied by f of n divided by b to the I. Okay, again, a to the I is the number of nodes we have. F of n divided by b to the I is the amount of work I do in one node. Now at the bottom, I have a to the h, number of nodes I have, multiplied by a constant. This is really the advantage here. I know the amount of work I'm doing at the leaf level. I don't really know how much work I'm doing at the rest. It's just f of n something. But here at the bottom, at the leaf level, I know that at every one of those leaves and every one of those base cases, I'm doing trivial work. I'm just returning. So, or doing something trivial in the sense that it's a constant computation. So the amount of work is going to be a to the h, which is the number of nodes, multiplied by constant. So let's put everything we described in one formulation. What's the total amount of time? Or if you'd like to talk again more accurately, what's the total number of steps we did in this tree expressed in the size of the input? So T of n is what we do at the bottom level. We know it's a to the h multiplied by a constant, T of 1, plus the rest. The rest is the summation of all the levels, from level 0, I equal to 0, till h minus 1, till the last level before the h. What am I doing in every level? It's a to the I, the number of nodes in that level, multiplied by the work I'm doing in every node. So it's a to the I multiplied by f, of n divided by b to the power of I. This is just, I'm restating what's in front of us, but in an equation form. Okay, the total number of steps I did in this recursive effort, or in this recursion tree, or in this recurrence tree, is what I do at the leaf level and everything above it. I'm splitting them into leaf and everything above it because I know at the leaf level exactly what I'm going to be doing. I will make use of that. So that's stated separately. It's a to the h by a constant. Everything above it, I'm using a summation. Why am I using a summation? Because it's actually a systematic sequence of terms that I can code using summations. They're all alike. It's the total number of nodes multiplied by the work as done in every node. Now we have already went into a lengthy discussion about the height of the tree and its dependency on the b, which is the denominator that you divide by the n. So we said the height is always going to be log n base b. So what I'm going to do is I'm going to substitute in the a to the h multiplied by a constant. I will remove the h because at the end what I'm trying to do here is to have all the terms n. so I could work them out mathematically and figure out what's the big O in terms of n. So I don't like the h. The h is causing me a trouble here, okay? So I will get rid of it by replacing it with log n base b. And again here the b is the term I'm using to divide the n by. So this is now my formulation. T of n is equal to a to the power of log n base b instead of h multiplied by a constant, and this is the amount of work we do at the leaf level plus the rest, which I already mentioned. I will play a trick with logarithmics here. I will swap the a and the n. I'm going to get the same answer. This is a valid logarithmic manipulation, so the equation becomes t of n equals n to the power of log a base b, and instead of a to the power of log n base b. That's what we're seeing here. T of n is equal to n multiplied to the power of log a base b multiplied by a constant. That's the amount of work I'm doing in the leaf level, plus the rest, the previous levels. Now, there are three possibilities here, given what we know from asymptotics. The first term, which is the amount of work we do at the leaf level, is asymptotically bigger than the second term, which is the rest of the tree. Or the first and second term are equal. I mean here by first and second, the two terms added together, the right hand side of my equation. So either the left is bigger, or they are equal, or the right is bigger. Okay? Second term is asymptotically bigger than first. Remember, what we are after is we are after the big O. So if one term is n and the other one is n squared, so we'll consider it n squared, because n squared will override, will be an upper bound for n. So what we're going to do is we will compare these two terms to figure out what is the relation between them. Is the first bigger than the second? Is the second bigger than the first? Or are they equal? So let's look at the three cases. In case one, the amount of work we do at the leaf level is the highest asymptotically compared to the rest of the tree. But since we are actually doing the division systematically, it will not be bigger than just the root. What we will see is a progression of increasing work. So this is what I try to highlight here. At level 0, way at the top of the tree, we did f of n. And then in the next level, we will do more work. So f of n is less than a of f of n by b, which is less than a squared of f of n by b squared, which is less than all the way till a to the I multiplied by f of n by b to the I. And finally, we reach the highest asymptotic order, which is at the leaf level. So there will be a progression of increasing work we are doing in all the levels, starting from the root until we do the biggest amount of work at the leaf level. Now, this might sound counterintuitive in the sense that the way we think of recursion, we start with the difficult part of the problem, or we do something that is demanding in processing, and then as we keep into recursion, going into recursion, we're kind of simplifying what we're working with until we hit the base case. But this is one way to think about recursion. Depending on the algorithm, you might be doing some work at the beginning, but as the recursion progresses, as you keep recursing into the method, you keep doing more work until you hit the base case, and then you're doing something really crazy at the base case, and you're doing, actually most of the time you're computing, or the computations you're doing are done at the base case. And this is what we're looking at here. The base case, the total amount of work in an asymptotic way of thinking, is going to be bigger than anything we have seen before while we are going from the root to that base case, or to that leaf level. Now, in the second case, every level is the same like any other level. So comparing the first one to the second one to the third one to the fourth one, all the way to the last one, they're all the same. So that would be my case 2. And in the third case, it's going to be the reverse of the first case. The biggest amount of work we do is at the root level. So we do a lot of work at the beginning. And as we keep progressing in recursion, we're doing less and less work. Until we hit the leaf level, where we're doing the least amount of work. Okay? So usually most people, when they think of recursion, they will think of it that way, but that's not necessarily true. As I mentioned, there are algorithms that will keep doing more work, and then the biggest amount of work will be done at the base case when we bottom the recursion. Okay? So here are the three cases, and they really will be derived from the logic, in the sense the logic of the algorithm will either be, the root level. At the beginning you do most of the work, or when you hit the base case you do most of the work, or you're always doing the same amount of work. So this is the time to remind you of the geometric series. If you remember from your school days and as well as university days, the geometric series takes the pattern of a plus a multiplied by r plus a multiplied by r squared plus a multiplied by r cubed, and so on. Okay? Now, if you plug in a equal to half and r equal to half, that's what you get at the top line. Why this is important? This is very important to us, as you will see. So it turns out that case 1, where the biggest asymptotic term is at the leaf level, is an increasing geometric series. Now, why are we getting an increasing geometric series again? Because we are doing the divisions in a systematic way. It's progressing from n to n by b to n by b squared, and we're doing the same number of branches. Okay? And ultimately we reach to the highest term at the leaf level. So we cannot have reached to it at the leaf level unless all what are before it are also increasing, starting from f of n at level 0, going all the way down to level h. So this is actually will turn out to be an increasing geometric series. Now, case 3, where the largest amount of work you do, or the biggest amount of work you do, is at the root level, and since you're also following the same systematic way of dividing the data into a branches, and then further into a branches and further into a branches, it is not possible that the first term is the biggest term and then the ones after it are a little bit smaller than it, and then suddenly you got a further drop at the leaf level. What you're looking at is a decreasing, again, geometric series, where the amount of work that you do going down in the tree will decrease, but in a monotonic way. It's not in any kind of arbitrary or random way. Okay? So, again, we have in the master method 3 cases. First term is asymptotically bigger than the second. This will be an increasing geometric series. First and second are asymptotically the same, and second term, which is third case, is second term is asymptotically bigger than the first, which is in the case of a decreasing geometric series. Now, let's look at this example we have seen before. Tn equal to 3 Tn by 4 plus theta of n squared. Let's look at the level sums. We started by n squared, and then n squared were decreasing as we go along. So it kept decreasing because you're multiplying by a fraction. It kept decreasing again and again until it reaches to n to the power of log 3 base 4. So what you see here actually is the first term must be bigger than the last term. The first term I mean at level 0, and the last term I mean at, or the level sum at level h. Okay? So this was a decreasing geometric series. Okay? Now, how do we use the master method without building this tree? Because I've already showed you the derivation of the recurrence, which is n to the power of log a base b multiplied by a constant plus this summation a to the I of n to the b divided by b to the I. Yeah, we got the idea, I hope, by now. But the question is, how can we avoid, for any specific piece of code, plotting the recurrence tree? and figuring out in a fast way the asymptotic order. Now, the three cases that we are looking at can be determined by comparing n to the power of log a base b and f of n. Why? Because if they are the same, if f of n is equal to the n to the power of log a base b, you should see the same term at the root of the tree and the level sum repeated at the bottom of the tree at the leaf level. If this is n squared, that has to be n squared. If this is n cubed, that has to be n cubed. And since we're doing a systematic division, it's impossible that in the middle it will change. Okay? So if the first one is n squared way at the root level, at level 0, and the last one is also n squared, as long as they agree in the asymptotic order, everything in between has to be the same asymptotic order. Okay? Now, if the one at the root level is asymptotically bigger than at the leaf level, then it must have been also decreasing asymptotically all the way till we reach the leaf level. In the reverse, if the one at the leaf level is bigger than the asymptotic order is bigger than the root level, then it must be increasing all the way till we reach the root level. So just comparing the root and the leaf level sums is enough to figure out, are we looking at an increasing geometric series or a decreasing geometric series, or if they are equal. Now, we're looking, if they are not equal, we're looking at an asymptotic difference, because this is a geometric series. The numbers increases dramatically between the levels, so there will be an asymptotic difference. So let's think math here. If I tell you that the leaf level is asymptotically bigger than the root level sums. So the level sum for the root level, comparing in the level sum for the leaf level, there is an asymptotic difference. What does that mean as an example? At the root level, at level 0, you see the level sum, say, n to the 3. And at the leaf level, we're talking about asymptotic difference. So at the leaf level, it's going to be like n to the 4, n to the 5. It cannot be n to the 3, otherwise they are equal. So if this is n to the 3 at the top, then at the leaf level it's going to be n to the 4, n to the 5, n to the 6, n to the 7. In other words, if you divide what's at the leaf level with what at the root level, in terms of level sums, you should get some n. You will divide n to the 5 at the leaf level by n to the 3 at the root level, you should get n to the 2. If at the leaf level is n to the 9, and at the root level is n to the 5, you divide n to the 5 by n to the n to the 9 by n to the 5, you get n to the 4. So the difference between them has to be in order of n, has to be a polynomial difference. That's the idea here. It has to be a polynomial difference. Okay? This is what this is saying. Dividing n to the power of log a base b by f of n, if it gives you a polynomial difference, which is n to some epsilon, where epsilon is greater than 0, then you are in case 1. Then you are in case 1. Okay? Which means that the leaf level is asymptotically bigger than the root level. Okay? Now, this is again an example. N cubed is polynomial larger than n squared. So if I divide n cubed, where did I get n cubed from? Is the amount of work I'm doing at the leaf level. Where did I get n squared from? It's the amount of work I'm doing at the root level. So the difference between them is polynomial. It's n. Okay? So if it's the case, then we are at case 1. This means that n to the power of log a base b is larger than f of n by factor of n to the epsilon. For some epsilon greater than 0. This means that if we take f of n, we need to multiply it with some power of n in order to match the gross of n to the power of log a base b. So n to the power of log a base b grows significantly larger, polynomially larger than f of n. And as a result, it would need to be multiplied by some power of n to match its rate of growth. So the ratio of n to the power of log a base b by f of n is an omega of n to the epsilon. This is what it means to say that n to the power of log a base b is polynomially larger than f of n. Now, using the big omega definition, we say that there exists a constant C1 such that the ratio of n to the power of log a base b divided by f of n is bounded from below by C1 multiplied by n to the epsilon. So using big O, when we say n to the power of log a minus epsilon grows polynomially larger than f of n, we mean that in order to get an order of growth equivalent to f of n, we need to start with the higher rate, which is of n to the power of log a base b, and subtract out some power epsilon, so we can reach the rate of growth which is proportional to f of n. So what I'm basically telling you here is, if we are in case 1, what's the big O? Okay? Now, we've already discussed why n to the power of log a base b divided by f of n will have to be some power of n. But let's swap the terms as the arrow shows. So f of n will be less than or equal n to the power of log a base b minus epsilon. There has to be a minus. We have to decrease the power of n to reach to f of n. Now, what that means is f of n is equal to O of n to the power of log a base b minus epsilon. Okay? Because without the minus epsilon, we are actually talking about the performance of the leaf level, the h level, the level h. But with the minus epsilon, we have decreased the performance. Okay, we are looking at a lower asymptotic order, which is that of f of n. So here is our conclusion. For case 1, if f of n is equal to O of n to the power of log a base b minus some epsilon, and we can find that epsilon. The thing is, we have to find this epsilon, okay? Then t of n is in theta of n to the power of log a base b. In other words, if f of n is polynomially smaller than n to the power of log a base b, in other words, again, stating this in a different way, if the root level performance is asymptotically less than the leaf level performance, then our performance really is dominated by what's done at the leaf level. So we will pick that to be our performance. It's in theta of that performance. Okay? Now, how do you figure that out? You will see examples. How do you figure the epsilon? You will see examples. But once you figure the epsilon and the relation between f of n and the n to the power of log a base b is minus epsilon, in order to make f of n equal to what the leaf level is, you have to grab the performance at the leaf level, subtract some power from it, and that will give you the performance of the root level. Then really the leaf level is dominating the performance, and it is the highest performance, it is the highest asymptotic order, and we will consider that as actually as our performance, which is the performance at the leaf level. Now in case 2, remember, they are equal. If what at the leaf level in terms of work is the same as the amount of work done at the root level, we can neither say that it's the leaf nor the root. It's both. It's everything actually in the tree. Everything in the tree means the height of the tree, because if I'm doing the same amount of work in all the levels of the tree, I have to multiply in order to describe the performance or the number of steps in relation to n that I'm doing in the whole tree. Since the root is not dominating and the leaf is not dominating, I have to figure out the amount of work I am doing at every level and multiply it by the number of levels. We know that the number of levels is going to be log n base b. Okay? Now, how much work are we doing in every level? Well, I could talk about it as f of n, but then I have a problem, which is that I would like to standardize my theorem here to be always based on log a base b and log a base b. So I will use the leaf level, and the leaf level is the same as the one before it, and the same as the one before it, and the same one as the root. So it's going to be n to the power of log a base b multiplied by log n. N to the power of log a base b is the amount of work you do at every level. Log n is the height of the tree. Okay? Now, in case 3, it's the reverse of case 1. Okay? If f of n is an omega of n to the power of log a base b plus some epsilon. In other words, the amount of work I'm doing at the root level is asymptotically bigger than the amount of work I'm doing at the leaf level. So if I divide f of n by n to the power of log a base b, I get some n, some polynomial difference. Okay, like for example, doing at the root level n to the 5, and doing at the leaf level n to the 3. So our work is bounded by n to the 5. Now, what's the epsilon here? It's 2. 5 and 3, the difference is 2. This is what the definition. Definition looks complex, but it's not. It's just a formal way of talking about what we are describing here mathematically. If I can equate what I'm doing at the leaf level by what I'm doing at the root level by adding some power to what I'm doing at the leaf level, this is what it means, n to the power of log a base b plus epsilon. The epsilon is adding some power, okay? Then I have made the leaf equal to the root. Then the root work, the amount of work I'm doing at the root level is bigger, is asymptotically bigger, okay? And that's why you see here it says t of n is equal to theta of f of n. What I'm doing at the root level will dominate our performance. Okay? Now, this summarizes the three cases. Okay? So either, in very plain, simple terms, either we pick the root to be the performance that is dominating, and this is case 3, or we pick the leaf to be the performance that is dominating, and that would be case 1, or they are equal. So here is the full picture. Here is the actual master theorem, you know, like it is stated in any textbook. Okay? Let me read it and then we will have some comments about it. It says, let t of n be a monotonically increasing function defined on a non-negative integers by the recurrence t of n is equal to a, the branching factor, multiplied by tn by b, the size of the divisions, plus f of n, some additional work we do. Where, as we said before, a is greater than or equal to 1, b is greater than 1, be constants, and let f of n be a function. Okay? Now, t of n can be bounded asymptotically in 3 cases. If f of n is equal to O of n to the power of log a base b minus epsilon for some constant epsilon that is greater than 0, then we are talking about the leaf level doing most of the work, or we are doing most of the work at the leaf level, then t of n is going to be the work done at the leaf level, which is n to the power of log a base b. Second case, they are equal, is going to be n to the power of log a base b multiplied by log n. Third case, which is the height of the tree. The third case, f of n is equal to the n to the power of log a base b plus some epsilon for some constant epsilon greater than 0. Then our performance is going to be theta of f of n. Now we add here one condition that we need to check for. What is the condition? See, in the third case, we are saying that the root level is doing more work than everything below it. So it is doing more work than the one after it, and the one after it is doing more work than the one after it, and the one after it is doing more work than the one after it. Okay? Until we reach to the leaf level. So there will be a polynomial difference between the root level and the leaf level in terms of performance. Okay? But we're going to set another assumption. The assumption is that the branching factor A multiplied by f of n by b is always less than or equal some constant multiplied by f of n. Which means the amount of work we do, given any child and parent, the amount of work we do at the child is less than or equal the amount of work we do at the parent. Okay? So it is decreasing as we go along, or staying the same, but generally it will be decreasing. Okay? So, why? We will see why, and we'll give this a name shortly. So again, the statement mentioned at the bottom of the slide here says that given any parent is f of n, the child of the parent or the children of the parent is going to be branches, A branches, each one I'm doing f of n by b work. So the A multiplied by f of n or by b has to be less than or equal some constant multiplied by f of n. Okay? For the constant between 0 and 1, by the way. Okay? So what that means is, at the child level, the children of any node should be doing less work, or equal work to the parent, shouldn't be doing more work. Because I want that to get the decreasing geometric series. And we will give this name, it's called the regularity condition. So you'll have to check for that, as you will see. And we have many examples in the tutorials about this. So you have to check for the regularity condition when you find yourself in case 3, that you are always doing less work, or equal, not more. But note, I have a C here, so I can multiply, can make the C as big as I can. It's going to range from 0 to 1. And that really translates to, since it's less than 1, that I should always be doing less work than C multiplied by f of n. Okay? Let's talk about this regularity condition. In case 3, we must have A multiplied by f of n divided by B is less than or equal some constant multiplied by f of n. And I've stated here very clearly the regularity condition to check that parent does at least as much as the children. Okay? You know, the above says that f of n, the amount of work done in the root, needs to be at least as big as the sum of the work done in the lower levels, if not more, of course. Okay? If not more. Now, where would we start to see violation of this? Look at the examples at the bottom. T of n equal to 2 Tn by 4 plus n. Okay? So I divide, the A is 2. I am considering out of the 4 divisions, where each division size is n by 4, I am considering 2 of those to continue with in the recursion. And then I do an additional n work. So every time I do work from one level to the next, I'm doing less work because I'm dividing by n by 4. So if I start with n equal to 100, next level n is going to be 25. Next level I'm going to take 1/4 of 25. Okay? So I'm always doing less work. And I have at every level I'm doing some n effort. But that will not make me exceed my parents. Now if you look at the next example, I have a funny function, the same recursive term 2Tn by 4 plus cosine n. Now cosine increases and decreases. Okay? So when it suddenly increases, we will be doing more work than the parent. And it will keep increasing, so we'll be doing more work than the parent. Okay? And then we do less work than the parent, and then we do more work than the parent. This is the nature of the cosine function. So there will be a violation of the regularity condition because sometimes we will be doing more work than the parent. Okay? So we're not really gaining by this. And obviously we cannot then, because we're going to be having increasing and decreasing values, we cannot just either refer to the leaf or the root to talk about the performance. Okay? Now, how do you apply all this? Let's look at the steps. First, you calculate what is n to the power of log a base b. How do you get it? Well, you have a and b from the recurrence, so obviously step 0 is to get the recurrence from the code. Okay? Or if it's given to you, then it's almost like plugging in a simple formula and doing the computation. Once you plugged in into the power of log a base b, you will try to rewrite the given f of n as either n to the power of log a base b minus epsilon or plus epsilon, or just as is. Okay? And from that you will determine which case you're looking at, if it's case 1, case 2, or case 3. Now if it's case 3, you check again for the regularity condition, which, according to what we're describing, the master theorem will not be able to help you if the regularity condition is violated. Now, if it's not a gap case and the regularity is not violated, then use the master method to determine the performance. So let's see an example. Tn is equal to 16 Tn by 4 plus n. So the A is equal to 16, the B is equal to 4. Let's compute n to the power of log a base b. That's n squared. Now f of n is n. The question is, can I rewrite f of n as in terms of n to the power of log a base b? Yes. The answer is yes, but I have to make the epsilon 1. So since here it's going to be minus epsilon, not plus epsilon, so it's case 1. Now case 1 says that the leaf level, or at the leaf level in the recursion tree or in the recurrence tree, we're doing an asymptotically bigger amount of work compared to the root level, compared to level 0. Consequently, that the dominating part of the performance is at the leaf level. Consequently, it is theta of n squared by just substituting in n to the power of log a base b. See how easy this is compared to doing a recurrence tree. As long as you are given the recurrence or you have found the recurrence from the recursive code, the rest is straightforward, simple, and arithmetical substitution. Okay? You just have to figure out, is this minus epsilon or plus epsilon? Do I need to subtract or do I need to add to the computed power from n to the power of log a base b? Let's see another example. You're given again the recurrence. T of n is equal to t 3n by 7 plus 1. Now the a here is 1. The b is the reverse, obviously, because it's initially a denominator. So if I extract it out, it's going to be 7 divided by 3. And n to the power of log a base b is n to the power of log 1 base 7 divided by 3, which is n to the 0, which is 1. Now I'm given that f of n is 1, and I've just found that at the leaf level it's 1. So all in between has to also be 1. So this is case 2. Okay? I have to find out all the work done in the tree level by level for all the levels, or node by node for all the levels. So it's going to be n to the power of log a base b multiplied by log n. Let's substitute in there. So n to the power of log a base b, we already found out that it is going to be 1. So that's 1 multiplied by log n, so this is going to be log n. Okay, again, notice how easy this is and straightforward. Let's look at this one. Tn equal to 2 tn by 2 plus n to the 4. So I'm splitting the data into 2 halves, and I have 2 branches. A is equal to 2, the denominator b equal to 2, and I'm doing additional work at every level, which is n to the 4. So let's do that. This is going to be n to the power of log a base b is equal to n. Okay, because the 1 will be the result from log 2 to the base 2. Now f of n is 4, or n to the 4. So the difference is plus epsilon or plus 2. Okay? Sorry, 3. The epsilon has to be 3 because n is 1. Difference between n to the power of 1 and n to the power of 4, the epsilon is 3, and it's a plus. So what that means, we are at case 3. At the root level, we're doing most of the work. You could argue this is intuitive because if you look at the formula, it says 2n by 2 plus n to the 4, but I don't want you to think intuitively. I want you to apply the formula and deduce it from the formula. This is obviously a plus epsilon, so we're looking at case 3. We're at the root level, we're doing most of the work, and we said if it's the case, it's going to be f of n, which is theta of n to the 4. Okay? Now, this is case 3. What about the regularity condition? Okay? Let's read the line at the bottom, the bullet at the bottom. It says, don't have to check answer using regularity condition because f of n is of the same form of n to the power of log a b, but only larger. Okay? So, you could still check the regularity condition, and you will find that we are meeting the regularity condition, but it is here intuitive because I have actually resolved n to the power of log a base b, and it turns out to be n, and the other term is n to the 4. So obviously the regularity condition is met because I'm doing less work as we go down. Now let's talk a little bit about this notion of gap cases, which I kind of mentioned in the formal definition of the master theorem, but I didn't elaborate much on. So between every 2 cases, between case 1 and case 2, there is what we call a gap. And between case 2 and case 3, there is also what we call a gap. Now, what is this notion of a gap? It's a situation where neither case 1 applies nor case 2 apply. Remember, case 1 was the leaf is doing most of the work. The leaf level have most of the work. In case 2, we said they are equal. So there is a gap between both of these guys. Okay? There is a gap where it's not that the leaf is doing most of the work, and it's not that they are equal. It's somewhere in between. Okay? Now, when will this happen? If f of n is smaller than n to the power of log a base b, when the amount of work we're doing at the root level is smaller than what the amount of work we're doing at the leaf level, but it's not polynomially smaller. So you cannot think of this as a geometric series. Okay. Now, if we have this situation, then we cannot use the master theorem right away. I will show you a better approach, later on, which is with the Akra-Bazzi theorem. So, if it's a gap case, we cannot apply it as is. Now, we could go and work around it and do some mathematical manipulation and do some approximations, and end up we will be able to approximate it to one of the two cases. But there is a better way, in my opinion, which is Akra-Bazzi, and that's what I want you to do. Okay. However, in the tutorial you will be seeing, what can we do with the gap cases as well, in trying to use the master theorem. So this is the first gap case. It has to be polynomial logic, basically, between the root and the leaf. Now, between case 2 and case 3 also there is a gap case. Okay. When, again, following the same way of thinking, when f of n, the amount of work we're doing at the root level, is larger than what we do at the leaf level, but it's not polynomially larger. It's not n to the 4 and n to the 3. Okay, it's n to the 4 and the other one is n to the 4, but much smaller n to the 4. Okay, so for those gap cases, again, we have an issue. We have an issue. Okay, so let's see, some gap example. Solve t of n equal to 2 tn by 2 plus n log n. So we're doing additional work in addition to the splits of the data. At every level, it's n log n. So n to the power of log a base b is equal to, the a is 2, as you see, the b is 2, as you see. So it's n to the power of log 2 base 2, which is n, because log 2 base 2 is 1. So f of n is n log n. Now, the difference between n log n and n is not polynomial. And here is the question I pose to you in order to make you appreciate this. Can we find epsilon such that f of n is equal to some omega n plus 1 epsilon? And the answer is no. Okay, and you can take the limit as I have showed you here, and you will see that this is actually not possible. Okay, so this is a gap case. So it doesn't have to be as naive as the same power n to the 7 and n to the 7, and there is a small difference between them. It could involve other mathematical functions like the log, and now we don't get polynomial difference. Okay, so some pitfalls of the master theorem. It works nicely if you have an increasing or decreasing geometric series, and or you're doing the same amount of work at every level. Okay, where does it not work? If t of n is not monotone, like for example saying t of n equal to sine x, or if f of n is not polynomial, like n divided by log n. Okay, so, and also b cannot be expressed as a constant, like square root of n. Okay, so all of these cases the master theorem will not work. Now, you might ask, okay, how popular or how useful is this theorem? Well, for most of the cases, actually, it is quite useful for a reason that when you design a divide and conquer algorithm, most likely, for at least for a lot of the simple, I would say on average difficulty problems, you will end up with a recursion that recurrence-wise is going to be an increasing or a decreasing geometric series. Unless you're doing something really, innovative or flawed or strange in the recursion, you will be able to use the master theorem, because when you write the recurrence, it will be something that is solved by the master theorem. Okay? But there are divide and conquer algorithms, there are recursive algorithms that are very complex, that cannot be solved by the master theorem. And you really don't have control here, because when you start writing a recursive algorithm to address a problem, you're not thinking, oh, I should actually write it so that it's solvable by the master theorem. You develop a solution, and it's based on your talent, how efficient the solution is, how correct the solution is, hopefully it is correct, and afterwards you start thinking of performance. Okay? So this makes the master theorem useful in many cases, but not in all cases, because you have no control, on any algorithm you develop, whether it's actually going to be, useful as a tool or not. I mean, the master theorem itself. Okay. because it has a lot of set conditions that it has to be met, and it has these gap cases and the regularity condition. Okay, so all of the following cannot be solved by the master theorem. Okay, 2 to the n, Tn by 2 plus n to the n. Here a is not a constant, it's 2 to the n. Okay, or the next one, 2 Tn by 2 plus n divided by log n. F of n here is not polynomial. Okay, now, or 0.5 t n divided by 2 plus n. Here a is less than 1. It has to be greater than or equal to 1. Or this is a nice one, 64t of n by 8 minus n squared log n. You know, this is not positive. Okay, so it's not even something we can start to address with the master theorem. Okay, or the last one, Tn by 2, that's okay, plus n 2 minus cosine n. So here the regularity condition will be violated, because you will go up and down because of the cosine function in terms of the values that would result from cosine n, or 2 minus cosine n. Sometimes you're doing more work than the parent, sometimes you're doing less work than the parent. So computer scientists have known for many, many years that the master theorem, even though it is the most popular theorem to analyze recursive code, has a problem. The problem is in the gap cases and regularity condition and the general format of the recurrence that must be satisfied in order to use the master theorem. And there has been many attempts to generalize the master theorem so that it could be used to solve the performance or calculate the performance of any recursive code. There are many generalizations actually. If you go to the Wikipedia page for master theorem, you'll find at the bottom a list of theorems that tries to generalize the master theorem. Interestingly, the most popular and the most accepted generalization or alternative, if you would like, to the master theorem is a theorem developed by two mathematicians from the American University in Beirut. Their names are as listed here, Muhammad Akra and Akra-Bazzi. And these guys were not computer scientists at all. Back, in the mid-1990s, they realized that computer scientists are facing a problem with recursive code, that they cannot analyze it that easily because the master theorem has lots of deficiencies, if you like. And because these guys are mathematicians, and they actually, their work prior to the Akra-Bazzi theorem was concentrated on solving and analyzing the performance of recurrences. So it's like a perfect match, two mathematicians with lots of expertise in working with recurrences, and they get exposed to a computer science problem, which is how to come up with a straightforward, simple, relatively simple way to come up or find the performance of any recursive code. So they write this paper and they publish it, and this becomes actually, up to now, the best generalization, and if you'd like, kind of the better approach to finding the performance of any recursive code, regardless of how complicated the recursion is, and regardless of the recurrence itself. You could here use any recurrence. So there are some really complicated algorithms in the graph theory area that use divide and conquer, and it is recursive, and you could easily come up with the performance by plugging in the terms in their equation that I'm going to show you. And even in your textbook, which is considered the classical textbook for the course, the Corman textbook, this is the only generalization they refer to as better than the master theorem. So it's quite interesting actually that we have this, and it's actually can help us a lot in doing any recurrence and solving any recurrence, and consequently analyzing any recursive code. And by the way, in an exam or a midterm or a quiz, I always allow students to use it right away, unless I ask you explicitly to draw and work the recurrence tree. If I don't specify it, then you can just, and if you're up to the math here, then you can just go and plug the numbers and use the Akra-Bazzi. So let me show you Akra-Bazzi. So the first thing to know about Akra-Bazzi is that it is made to solve summations of recurrences. So you could solve something like the example that appears at the bottom of the slide. Something like 2tn divided by 3 plus 4tn by 7. Okay, we haven't seen this before with the master theorem. Okay, plus some additional work, f of n, which is here n squared. Okay, so you can have a summation of, or a series of recurrence terms that are summed together, and it will actually help you in solving this. Do we have actually code that maps to 2tn by 3 plus 4tn by 7? Yes, as I mentioned, in the graph theory area, there are some really advanced algorithms that if you try to write the recurrence for it, it will be something like this or even more complex than this. So how did they go about it? Well, they said, okay, since we are trying to solve summations of recurrences, let's model it as, well, guess what? From your calculus days, as calculating the area under a curve. Okay? Now, the proof for this is beyond this course, and I link the proof in the last slide to you if you'd like. And you know, it's written in a formal mathematical notation. It's about 80 pages, so I'm not going to really require you to learn this because it's beyond the scope of this course. But if you're interested, you can go and check it out. But in basic, very simple, terms, what they did is they converted the problem of summing recurrences to an integration problem. The proof that actually this works is in the document I was referring to. Okay? Now remember, calculating area under the curve is nothing but summing areas. So they had to prove that that's the case, and that's what they actually proved. You know, that they could do integration using certain limits, and that is equivalent to solving the summation of recurrences. So let's look again at the general recurrence form that Akra-Bazzi solved, because we're going to use some of the parameters here. It says the summation of the recurrence from I equal to 1 to k, a sub I, or the branching, multiplied by t of n by b to the I, plus f of n. The constraints are k is a constant, so it does not change while the algorithm is running. A sub I greater than 0, b sub I greater than 1, and they are constants for all. F of n is bounded between n to the c and n to the d, where c is less than or equal to d. This is not really saying or setting any strict constraints that will prevent us from solving any recurrence, as you will see. So what they proved, their kind of theorem states the following: that if you can write the recurrence as in the previous formulation we discussed in the previous slide, t of n, the O that you're looking for, or the theta that you're looking for, is the following. It's n to the tau multiplied by 1, the integration from 1 to n of f of u divided by u to the tau plus 1 du. Now obviously here this requires you to do integration, and that's why some students will shy away from using this technique, although it is actually super fast to come up with t of n using Akra-Bazzi. Now really the new part here is, how do we find the tau? Now tau is the unique solution to the equation that is shown below, the summation of y equal from 1 to k, a sub I, b sub I to the power of tau equal 1. Where do I get the a and the b? From the recurrence itself. Where do I get the k? Again from the recurrence itself. Tau is actually what we try to solve. Okay? So the rest is straightforward, plugging in this formula and solving by doing integration first and then solving. So let's see an example of applying Akra-Bazzi. So suppose you have this recursive function where you're doing two-way recursion. And because of the way you're doing the two-way recursion, when you write down the recurrence, it comes up something like this. T 3n by 4 plus t n by 4 plus n. Now, the first step in doing Akra-Bazzi is to find tau. To find tau, I will multiply from every recurrence term the a and the b while raising the b to the tau, and then setting all this equal to 1. If you again would like a refresher of what we talked about in the previous slide, look at the bottom left of this slide. It says the summation from I equal to 1 to k of a sub I multiplied by b sub I raised to the power of tau. All of this set equal to 1, and you solve for tau. Let's apply this on the recurrent we have here, on the recurrence we have here in the top line. The a is 1, the b is 3 divided by 4 in the first term, and in the second term the a is 1 and the b is 1 over 4. I raise, since it's 1s, the a doesn't really appear here, I raise the b to the power of tau, so 3 divided by 4 to the power of tau plus 1 divided by 4 to the power of tau equal to 1. Now solve for tau. This is a trivial example, of course. The answer is tau equal to 1. I plug in now this 1 instead of the tau I have in my original formula. The original formula is at the bottom right, so it's going to be n to the 1. That's what you see in the center of the screen, multiplied by 1 plus the integration of 1 to n. F of u is going to be n divided by n tau plus 1. So this is going to be n. 1 plus 1 is 2, so it's 1, or basically u divided by u squared, or if you like n divided by n squared. So u, let's keep it u. U divided by u squared is going to be 1 over u. And then the rest is you do the integration. Now you get the answer is n log n. Let's look at this second example. I have this weird looking recurrence. 1 over 4, that's the a, multiplied by tn by 4 plus 3 by 4 multiplied by 3 t3n by 4 plus 1. Again, my first step in applying Akra-Bazzi is to find the tau. I will multiply the a by the b raised to the tau plus a by the b raised to the tau from the second term. So in the first term, the a is 1 over 4, and the b also happens to be 1 over 4. I will raise the b to the power of tau. In the second term, which starts with 3 over 4, the whole term is 3 over 4 multiplied by t3n by 4. The a is 3 over 4, and the tau is also 3 over, and the b is also 3 over 4. I will raise that to the power of tau. Both of them, I will set the addition equal to 1, and now I solve for tau. And this will have the solution 0. Okay? Now, because I have to use 0, so it becomes 1 over 4 plus 3 over 4. Now, knowing tau is 0, I substitute n to the 0 is 1, and then the rest is straightforward. Okay, I'm sure you can do it by substituting tau is 0. Okay? Now, and then you solve, you integrate, and you see how easy this is. This is going to be theta of log n. Another one. This is a simple one. Tn equal to 3 tn by 2 plus n squared. Okay? So the tau obviously is equal to log 3. Now you substitute, it's going to be n to the power of log 3, 1 plus 1, integration from 1 to n, mu 1 plus log 3, and then you integrate and solve, and you will end up getting it in theta of n squared. These are the references for today's lecture. I have covered recursion tree, the master method, so I'm putting here Goodrich as well as Corman. Again, start with Goodrich and then move to Corman. Okay, the recursion tree is very well described in Corman, so stick to the reading there. And there is also a description of the recurrent analysis of merge sort, which I covered in the beginning of today's lecture. So I've put you the references for again Goodrich and Corman. And this is the proof for the Akra-Bazzi. If you get too interested about it, you can watch it, but this is not part of the course content. It's a little bit dense in terms of maths, but it's very interesting. And I've also put you the reference that exists for the Akra-Bazzi in the Corman textbook, which, as I mentioned, is the classical textbook for this course all over the world. So it's interesting to read. But again, you're not responsible for the proof. And you can download the text from the link at the bottom.